Welcome back. This is the second part of our section 1.2 video. Just want to record these names for posterity. I'll call this the product property. I'll call this the quotient property. This one will be the nested exponents property. I'm going to write nesting. Nesting property. And these two don't really have names, but it's just anything to the first power is the same number. And as long as the base isn't 0, write that down here, b is not equal to 0, then the base to 0 is 1. I'd like to, we'll learn a few more exponent properties in a bit and see some complex examples. But before we do, I just want to warn you on day one here, there is a place where students always go foul with distribution. If I write, let's call this the distributive property. If I write 2 times x plus y, that's 2x plus 2y. We're saying I can distribute the 2 to the x and the y. And that's because when I write 2 copies of x plus y, addition or multiplication by 2 is shorthand for addition twice. So 2x plus y is shorthand for x plus y times, or plus, sorry, x plus y. Which means that we have 2 copies of x and 2 copies of y. I'm using the fact that addition is commutative. I can take the 2 copies of x and write them down first, the 2 copies of y and write them down second. And the answer doesn't change, even though I rearranged the order of the addends. So I have 2 copies of x, that's 2x, 2 copies of y, that's 2y. There was nothing special about 2, this would be 3 or 4 or 10. That's the distributive property, and this is why it works. It's because I have addition inside, and multiplication is repeated addition. Well, since exponents are repeated multiplication, I can do the same thing with them. If I have, say, x times y on the inside, and I take that to the 3rd power, what's going to happen here? Well, this is shorthand for 3 copies of xy multiplied together. I can change the order without changing anything. I'm going to write the 3 x's and then the 3 y's. Commutative property. Well, that's 3 copies of x is x cubed, and 3 copies of y is y cubed. And there was nothing special about the 3. This would work with any exponent, 2 or 4 or 10 or -6 or 5 halves even. So we can distribute multiplication over addition because multiplication is repeated addition. We can distribute exponents over multiplication because exponents are repeated multiplication. These two situations are analogous to each other. They're symmetric even, you could say. What I cannot do is distribute an exponent over addition. X plus y squared is not equal to x squared plus y squared. Be very careful that you do not make this mistake. I see this a whole bunch in this class. This is one of the easiest ways to mess up a computation. See, x plus y squared, I have to do something else. I have to say, well, that's 1 copy of x plus y multiplied by another copy of x plus y. Let's get rid of that exponent and write down by its definition. X plus y times x plus y? What could that be? We'll have to FOIL that if you remember what that means. Let me do it the long way for now, and we'll learn a faster way in a bit. I'm going to distribute this to each of these. So it's x plus y times x plus x plus y times y. When I said I could distribute anything to this x plus y, 2 times x plus y is 2x plus 2y. I meant anything. In this case, the 2 is in x plus y. So you see down here, it's like this x plus y took the place of that 2 from upstairs. Well, now I have x times x plus y, right? I'm going to distribute the x to the x plus y. So that's x times x plus x times y. And then over here, I'll distribute the y to the x plus y. So that's x times y plus y times y. I can write some shorthand for repeated multiplication. X times x is x squared. I have 2 copies of xy, so I can just write 2xy. And I have 2 copies of y, so that's y squared. So this is the difference. There's an extra term in the middle. It's not just x squared plus y squared, it's x squared plus 2xy plus y squared. Be very careful not to make that mistake. I can distribute an exponent over multiplication, or I can distribute multiplication over addition, but I cannot distribute an exponent over addition. So be very careful. Okay. What else do I want to show you right now? Sure. Let's do a couple of examples of all of the rules we've seen so far. Let me try to evaluate about 5 to the negative 3, 5 to the 5th, 5 to the 1st. Well, let's make this a negative one. Well, when I just had one multiplication, I could replace it with addition in the exponent. So I can write this as 5 to the negative 3 plus 5 times 5 to the negative 1. But now I can use that rule again. This is 5 to the power of negative 3 plus 5 plus negative 1. That's 5 to the 1st power, which is 5. So in the future, we don't need to do this as 2 different steps. We can do it all at once. Each of these multiplications outside becomes an addition inside. Let's see. If I asked you to find me what is 3 to the 4th times 3 to the negative 2 divided by 3 to the 5th times 3 to the negative 3, what's that going to be? Well, 4 plus minus 2 and 5 plus minus 3 are my new exponents. So this is 3 squared divided by 3 squared, and that's equal to 1. There are a lot of different ways to solve this problem. Pause it and see if you can come up with one of your own. Welcome back. I do want to point out this product property only works if you have the same base. So if I write something like 5 squared times 3 to the negative 1 and times 2 to the 4th times 5 to the negative 1 times 2 to the negative 2. Here's our third example. I can combine the 5 squared and the 5 to the negative 1. I can combine the 2 to the 4th and the 2 to the negative 2. The 3 to the negative 1 is lonely, but I can't combine anything more than that. These have different bases, so I can't mix them. So I'm going to end up with, well, that's 5 to the 1st power, so I'll just write 5. This is 2 squared, so I'll just write 4. This is 3 to the negative 1. Now let's see, 5 times 4 is 20. And when I multiply by 3 to the negative 1, that's the same as dividing by 3, because 3 to the negative 1 is 1/3. So this is our final answer. In fact, it's really handy to think of fractions as just being a special kind of multiplication. Instead of writing 5 halves, for example, I could write 5 times 2 to the negative 1. Why would I ever want that? Take a look at this expression. How about x divided by 4 all over y halves? What in the world is that going to turn out to be? This is called a compound fraction, and they can be really daunting if you're not used to them. But they get a lot easier when you realize that division and fractions, well, fractions and division mean the same thing, and they're just special cases of multiplication. It's really just x fourths is really just the same as x times 4 to the negative 1. And y divided by 2 is really just the same as y times 2 to the negative 1. But I can take this a step further, and I can say this is really just the same as the numerator times the denominator to negative 1. Like this. And now instead of this confusing compound fraction, I've got an expression with no fractions in it at all. I can distribute this exponent to each of these two terms. I'm doing this the long way. What you're going to see a lot in these lectures is I'll show every step possible just to make sure that we don't lose everyone. But in the future, you'll be able to skip some steps. The things I write on the paper are not mathematics. So let's see, I'm distributing this -1. The things I write on the paper here are not mathematics. Mathematics is what's happening in our heads as we're doing this. So here I've taken this -1 and I've distributed it to both of these guys. The things we write on the paper are just to keep the mathematics flowing smoothly in our heads and to keep us from getting lost and so that we can keep our place. So in the future, if you know where this is going to go next, you don't have to write every step. See, nested exponents are the same as multiplying exponents. So 2 to the -1 to the power of -1 is the same as 2 to the power of -1 times -1, which is just 2 to the first power. So 2. So this is x times 4 to the -1 times y to the -1 times 2, which is equal to x times 2. These things with negative exponents live in the denominator. And I can cancel out. Since these are multiplied, my final answer is going to be x over 2y. That's a lot simpler than x fourths divided by y halves. So if you get stuck with one of these nasty expressions, you can always simplify things by remembering division is just a special case of multiplication by something with a negative exponent. Makes life a little more bearable. Let's see. On Courseden, you might have noticed that there are study guides for your 4 tests and your final exam. The actual final exam is very similar to the study guide. So I want to go over 3 questions that are like the first 3 questions on the study guide, so that you'll be ready when you see questions like this on the final. What if I said I had 1 over p to the -4? What would that be? Well, this is the same as p to the -4 to the -1, right? And that's nested exponents, so it's p to the power of -4 times -1, which is p to the 4. An exponent of -4 in the denominator is the same as an exponent of +4 in the numerator. In the future, you can just go from the first step to the last step now that you see that. If you see the pattern, that means if I wrote 1 over q to the -8, that'd be equal to q to the power of 8. Do you see? 1 over n to the 7th would be n to the -7. So if you just want to flip something from the numerator to the denominator or vice versa, all you got to do is flip its sign. Excuse me. All right, let's tackle some problems like the one on the final. If I asked you to simplify -3x to the -4 times 4x to the -2 y cubed, all cubed, what would we do with that? What would we do with that? Well, first thing I'll do is distribute these exponents to everything that's multiplied. I'm drawing in little multiplication signs so I remember what all my factors are. So I'm going to have a -3 to the -4 times an x to the -4. And over here I'm going to have a 4 cubed, an x to the -2 cubed, and a y cubed. See? This 3 went to each of these 3 factors because I can distribute exponents over multiplication, right? Let's see, -3 to the 4th power would be 81. So -3 to the -4th power is 1 over 81. See, -3 times -3 times -3 times -3. There's a shortcut here. That's this pair of minus signs cancels, and this pair of minus signs cancels. So the final answer is positive. So it would be 81, but this minus sign right here is going to put that in the denominator. So this first term is 1 over 81. X to the negative 4 is 1 over, x to the 4th. 4 cubed is 64. These are nested exponents, so I can multiply. This will be negative 2 times 3 is negative 6. 3 times 3 is 9. Okay. So I have 4 x's in the denominator, and here I have 6 x's in the denominator. Altogether, there will be 10 x's in the denominator. So the 64 and the y to the 9th live in the numerator. The 81 and an x to the 10th live in the denominator. So x to the negative 6th is 1 over x to the 6th. 1 over x to the 4 times 1 over x to the 6th. And look at it this way, it's 1 over x to the 4th times x to the 6th, and that's 1 over x to the 4 plus 6, see? So that's where I'm getting this 10 from, and that's my final answer. Looks a lot simpler than what we started with. Here's another example. And again, remember, you can pause this video at any time if you need a little more time to take in the work. Okay, here's a big one. Let's say my problem was all of this is going to be to the power of negative 2. On the inside, I have a fraction. 14a squared b to the 7th divided by 2a to the 5th b. Now, I have 6 factors here, 3 in the numerator and 3 in the denominator. I could distribute this minus 2 to all 6 factors. But I think I'm going to have a much easier time if I cancel out what's inside first. So here, 14 divided by 2 is 7, yeah? What's a squared over a to the 5th? Well, a to the 2 minus 5, that's a to the negative 3. And b to the 7th divided by b, remember b is the same as b to the 1st. So 7 minus 1 is 6. This will be b to the 6, because I had, this is the quotient property. This whole thing goes to the power of negative 2, so I'll take each thing to the power of negative 2. 7 squared is 49, so 7 to the negative 2 is 1 over 49. This is a to the negative 3 to the power of negative 2. This is b to the 6 to the power of negative 2. And if you remember your nested exponents property, you don't even have to write that step. We can use the nesting property to go straight to 1 over 49, a to the positive 6. So negative 3 times negative 2 is positive 6. 6 times negative 2 is negative 12. And this will look a little bit neater if we say, well, that means the a lives in the numerator, and the 49 and the b's live in the denominator. So we'll put the b's down here with a positive exponent. I flipped them from the numerator and the denominator, so the exponent goes from negative to positive. So this is a nice, much simpler final answer than what we started with. And the reason we practice doing this is that way when you're working story problems and you get complicated expressions like the top one, you can turn them into simple expressions like the bottom one. Now, I only have one more thing to show you, and then we'll be on to section 1.3. I just want to, it's marginally related to what we've been doing, and it's handy for reading papers. So the last thing in section 1.2 is scientific notation. A scientist might make note of the fact that the sun is 93 million miles away, and that's why it looks so small. But if I'm writing a paper about the sun and I have to quote this number 3 or 4 times, my little pinky is going to get tired of hitting the 0 key. Now, I'm sure you know something like this. When I write 570, that's the same as 57 times 10. 57 times 10 times 10 would be equal to 5,700. Do you see the pattern? Every time I multiply by 10, I'm adding a 0 onto the number. So if there are 6 zeros here, then instead of writing 93 million, I could write 93 times 10 to the 6th power. I multiply by 10 6 times to get from 93 to 93 million. The way I got that 6, I just counted all of these digits. So that's basically the trick of scientific notation, is you can write things as multiplied by powers of 10 so that you don't have to write such big numbers. Now scientists are going to do one more thing. Instead of writing 93 times 10 to the 6th, they're going to write, well, 93 is 9.3 times 10. So instead they could write 9.3 times 10 to the 7th. And the reason for that is they like this number, we call this the coefficient because it's multiplied by the other thing. They like the coefficient to be at least as big as 1, but never as big as 10. So instead of having a coefficient of 93, they're much more comfortable, scientists are, with a number between 1 and 10. 9.3 fits the bill. So 9.3 times 10 to the 7th miles is how a scientist would write this. Incidentally, if you're on your calculator and you get an answer of 93 million miles, your calculator might display this as 9.3 E7. What your calculator's doing is, it's shorthand for 9.3, and then the 10 has an E for exponent of 7. So this is the calculator's way of writing 9.3 times 10 to the 7th. So if you're working a math problem and your calculator says that the answer is 1.4 E11, well, that's really the same thing as 1.4 times 10 to the 11th, which is, well, the first 10 changes it to 14, and then there's 10 more 10s, so this 14 is going to get 10 zeros. I'll put commas every 3 digits so I can pronounce it. Looks like we're looking at 140 billion is our answer. So scientific notation is how a lot of these old calculators, and even some new ones, will display really big or really small numbers. Because scientific notation is great for small numbers as well. A red blood cell in your body, you've got billions of them, and each one is 8 micrometers in diameter. A micrometer is a millionth of a meter. So in other words, what I'm saying is, if you've got a red blood cell here, they're kind of donut shaped, except the divot in the middle doesn't quite go all the way through. This red blood cell, the distance from end to end is 8 divided by 1 million meters. Well, instead of saying, whoops, lost a 0 somewhere, 8 divided by 1 million meters, there we go. A scientist isn't going to want to write that, and they're definitely not going to want to write 0.000008. So instead, to write this in scientific notation, I have to move that decimal point 1, 2, 3, 4, 5, 6 places to the right, and if I do, I get 8. And I had to add 6 powers of 10, so this 8 is missing 6 powers of 10. Or in other words, down here with this fraction, I had to divide by 10 6 times. So I'm going to write that a red blood cell is 8 times 10 to the negative 6th meters in diameter, and that's scientific notation. I went with 8 times 10 to the 6th instead of 0.8 times 10 to the negative 5th, because 0.8 isn't between 1 and 10, but 8 is between 1 and 10. There will always be one way to write the number, such that this number here this coefficient is between 1 and 10. Your calculator would write this as 8e negative 6. Here's one more example. Here's a neat thing you can do with scientific notation. I don't know if you know this, but Well, of course you do. Everyone knows light is the fastest thing in the universe. But it doesn't move infinitely fast. It has a finite speed. The speed of light is 6.7 times 10 to the 8th miles per hour. The speed of light is 6.7 times 10 to the 8th miles per hour. So that's 6, a 7, and 7 zeros. I guess that would be 670 million miles per hour. So very fast. Now there's a concept in astronomy. Since space is so huge, it doesn't make a ton of sense to talk about things in miles or kilometers. There would be way too many of them. It would be ridiculous. So instead, a common unit of distance in space is the light year. It's the distance that light can travel in one whole year. Now, if it goes 670 million miles in 1 hour, it's going to go a very long way in a year. Let's find out how many miles in a light year. Well, I'm looking at hours here. I want to know years. Keep in mind the equation, distance is equal to rate times time. So if I know the speed of light, that's going to be my 6.7 times 10 to the 8th. The time is going to be 1 year. If I can write that time in terms of hours, we'll find out how long a light year is. So this distance of how far light can go in 1 year, first I need to know how many hours are in a year. Now a year is 365 days, and a day is 24 hours. So a year is 8,760 hours. So if we go 670 million miles every hour, and we do that 8,760 times, that's going to tell us how long a light year is. But here's the cool thing that scientific notation can do. 8,760, well, that's just 8.76 times 10 cubed. So when I multiply these two together, distance is rate times time, so it's 6.7 times 10 to the 8th times 8.76 times 10 cubed. 10 to the 8th times 10 cubed is just 10 to the 11th. So all I need to do is multiply 6.7 times 8.76. And that'll get me my answer. Those two numbers multiplied together get me a 58.692 times 10 to the 11th. But this number isn't between 1 and 10. So I'm going to take a power of 10 away from here and donate it over here. So instead of writing 58 times 10 to the 11th, I'll write 5.8692 times 10 to the 12th. And that is how many miles are in a light year. Do you see that? It's kind of a neat trick. Let me show you that trick a couple more times. If I had, let's say I had 1.6 times 10 to the 8th, and I wanted to multiply that by 5 times 10 to the negative 3. Then what I could say is 1.6 times 5 is 8, and 10 to the 8th times 10 to the negative 3rd is 10 to the 5th. So my final answer is 8 times 10 to the 5th. A lot easier than saying, well, this is 160000000, and this is 0.005. And now we'll type those into our calculator and pray that our finger doesn't slip. I like this method a lot better. Works with division as well. If I said I want to know what is 8 times 10 to the 5th divided by 4 times 10 squared, well, I can say 8 divided by 4 is 2, And 10 to the 5th divided by 10 squared, quotient property tells me that's 10 to the 5 minus 2. So this is 2 times 10 cubed, or 2,000. A lot easier than trying to type 80,000 divided by 400, and again, hoping your finger doesn't slip. I guess that top one would be 800,000, not 80,000. But anyway, that's scientific notation. Now you know. So that's all for now. We'll come back next with section 1.3, and that's where we're going to learn about square roots and their friends. I'll see you shortly.